Okay, so this is part 2 of lecture 7. So the three effects that we digested, relativity of simultaneity, time dilation, and length contraction, first of all, they all have to work together, okay? But second, and this is what the subject of this video is about, that they're not compatible with Galilean transformations. It would be a good idea for you to pause the video right now and to think for yourself, why is that? So for one thing, they assume the flow of time to be the same in all co-moving inertial frames. We're focusing on inertial frames. So if two events are simultaneous in one frame, with delta t is 0 in that frame, then they will have to be simultaneous in the other, delta t prime equals 0. Now, the idea of the speed of light being constant in all frames is not built into Galilean transformations as well. It treats light speed as any other speeds, and it applies velocity addition rule to all motion. Galilean transformations can't possibly predict moving objects to be shorter than objects at rest. So let's say I measure the length of some object in frame S, okay? For example, let's say it's moving. Yesterday, we talked about measurement of length by measurement of time, using measurement of time. We're marking the time when the rod started passing and ended passing a particular mark. That's one way of making a length measurement, but really I was measuring time. I can also make measure the length of something by simultaneously marking the positions of both ends of the object. Let's say there's a rod is moving, and I cut with a laser beam the two marks that mark the positions of both of its ends. Of course, I have to do it at the same time. Okay, forget special relativity. If you have a moving object and you want to measure its length, you have to measure the positions of both ends at the same time, obviously. So I do it by making a measurement of simultaneous events. One end of the object is aligned with the ruler at position x1. The other end is aligned with the ruler at position x2 at the same time. Then delta L is defined to be x2 minus x1, spatial separation between simultaneous events at time t. Okay, and if you use Galilean transformation, then you will see that delta L prime will be equal to delta L. Remember Galilean transformation. We have x prime equals x minus vt, so x prime 1, and then x prime. So here's my coordinate, s with x and for example y, and I have some kind of a ruler or some kind of a rod, sorry, moving, and I simultaneously mark locations with a laser beam, and I call this x1 minus x2, and so I say, aha, delta L equals x2 minus x1, very usual stuff. But then if you take this into account, this suggests that x2 prime minus x1 prime equals x2 minus x1, since both measurements were made at the same time. Okay, so I can even do this. T1 equals T2. We have two events. They're simultaneous in frame S, and so T1 equals T2, and therefore when you subtract x1 prime minus x2 prime, you get x1 minus x2. x2 minus x1 equals x2 prime minus x1 prime. And so you would find that delta L prime equals delta L. I'm not saying anything groundbreaking right now. So my point is that Galilean transformations, as they are, they can't possibly predict length contraction, they cannot possibly predict time dilation. They're inconsistent with the idea of speed of light being the same in all frames. And in short, Galilean transformations are incompatible with the special relativity effect that we discussed in the last several lectures, and we need a replacement. I want to remind you that what's the core reason for all those effects? Why do they happen? Pause the video right now. It's a very important question. Why? Where do all those effects come from? They all come from the idea that speed of light is the same in all frames. Okay? So we need to find a transformation, coordinate time in one frame to coordinate in time in another frame, that's compatible with special relativity, that's compatible with the idea of speed of light being the same in all frames, that includes in them all those effects, special cases, and so on. Now, there are many ways to do that. And your textbook does a wonderful job at deriving those new kinds of transformations. I will not derive them here. Again, there is no such thing as a derivation. There's only solving a problem. And my problem at hand right now is to find a correct transformation that's compatible with special relativity. It's not a derivation, it's a problem. It's a pressing problem. But I'm not going to do it here. I'm just going to state the correct transformations. So in summary, we need transformations between transformations of positions of coordinates and times between two co-moving inertial reference frames. They go by the name of Lorentz transformations. Now, you remember Lorentz found them before Einstein came along. He found them as just a peculiar feature of Maxwell's equations that leaves those equations invariant. Okay? But it wasn't clear if they're correct. People weren't sure if Maxwell's equations are correct, despite the fact that they describe experiments very well. But he found those transformations. And now we will see, and now it turns out that they come out organically from the postulates of special relativity. Again, I'm not going to show you on the video how that's done. You can either read the textbook. The textbook has a wonderful derivation of Lorentz transformations. All of these derivations, they're rooted in the postulates of special relativity, and these correct transformations come out organically. So what are they? Okay. So what I'm going to do is I'm going to remind you of the scenario. So this is frame S, and has coordinates x and y and time t. This is frame S prime, has coordinates x, y, and time t prime. We've already, hopefully, you're convinced that t is not the same as t prime. There's not a universal time. It's all personal. I live in my frame, I have my rulers and my clocks, and in my frame I measure x, y, z, and t. And a passerby or a spaceship that's passing by has their own rulers, their own clocks. It's personal, okay? And let's say that this is moving with speed v. By the way, v doesn't have to be positive. V can be either positive or negative. V is a velocity. And in one dimension, the directionality of velocity is encoded in the sign of a v, SIG. And we set times in both coordinates to be 0 when the origins pass by each other. Okay, I'm not making that mistake now. When the So now I'm going to divide the screen into two parts. Remember how we came up with the Galilean transformation? It's not even a derivation, it's kind of a common sense. Let's say there's an event, some kind of an explosion. It's located at coordinate x prime. This distance was vt. So x is x prime plus vt. And again, v can be negative. Of course, that means that the time when this happens also has to be negative because the origins coincide at t equals 0. But don't worry about it. The point is that this works even for negative v. And so we found that x equals x prime plus vt. And we didn't bother with time, but we can also say this. Okay, we didn't bother with that. It's obvious, it's redundant, it doesn't do anything. But this is also nice because it relates coordinates and times in frame S to coordinates and times in frame S prime. Okay. And you might recall that, well, not you might recall, but you can see that I can rearrange terms in the equations. And if I know everything about x and t, and I want to know x prime and t prime, I can do that. Right? So I can go in reverse. I forgot to put a t prime here. So the forward transformation is this. If I know about the situation in frame S prime, I can calculate the situation in frame S, and vice versa. If I know the situation in frame S, I can calculate the situation in frame S prime. But it's okay, maybe this is obvious. Now I'm just going to state the Lorentz transformation. So this is Galilean transformation. And this is Lorentz transformation. So what is the Lorentz transformation for coordinate? It reads the following. This is gamma. A little bit better. So you can see it will automatically include length contraction in it. So there's a factor gamma. Otherwise, it looks the same as Galilean transformation, but it rescales our rulers. If something is moving relative to each other, gamma is not 1, and it will rescale the ruler. And the interesting thing now is that there is a transformation on the time. That one is a little bit less trivial, a little bit less pleasing also to the eye. Okay, so this is a big deal. And again, this relates everything towards and times in S to chords and times in S prime. And true, there's also reverse transformation. Okay, and the reverse transformation is x prime equals gamma x minus vt, and t prime equals, we just reverse the sign in front of the v, gamma minus v over c squared x plus prime. There's often a lot of confusion related to the forward and reverse transformation. Something along the lines like which one is S, which one is S prime. And students are phenomenal at coming up with mnemonic patterns to memorize things. First of all, you don't have to memorize anything right now. I want to free you of all those mnemonic patterns. The idea is this. You have one frame and another frame, S and S prime, frame A, frame B, chocolate and vanilla. Doesn't matter. You have a frame and another frame. If the transformation from this frame to the other includes the positive sign, the plus sign in front of V, then the transformation from the other to the one will include the minus sign of V. If the transformation from the other to the one includes the plus sign of V, then the transformation from the one to the other includes the minus sign in front of V, not V. V itself can be either positive or negative. So again, if transformation from one frame to the other includes a plus sign in front of V, then from the other to the one, it will be a minus sign. And that's really the only thing you have to remember. Don't worry about anything else, and then all those confusions will disappear. So this is Lorentz transformation. I will have more to say about them. For now, just take it as a fact. And these are completely compatible with special relativity. So let's go back. Let's put them to use right away. Let's go back to the example that we did first thing today with Alice and Bob. So here is Bob. And again, Bob's perspective. This reads 0. This one here reads 0. And this is Alice moving. This reads 0 by construction, but the question was, what does this read? And you saw that in order to answer this question, it was not a one-stepper. We had to first find the distance between Bob's windows, and then having found that, then we had to think about snapshots. So it was neither directly a time dilation nor a length contraction problem. It was a problem that we could use those two effects together to answer the question. Now let's try to apply Lorentz transformations to solve this problem. The question again. Now, what do we know? We know the following. So for event 1, we know everything. We know x equals x prime equals 0, and t equals t prime equals 0. We know everything about event 1. What about event 2? We know that x prime equals 50 meters because that's the position of the front of Alice's ship. We know that's 50 meters. According to her, she's at rest with the ship, so it's at the very front of her ship, which is 50 meters long. We know that the t equals 0. So Bob knows that his clock here at event 2 it's 0. So we have kind of a mixed information. So let me just write down Lorentz transformations again, and then it will become easier which one, it will be easy to see which one we have to use. But really, before I write that down, please understand that each pair of transformations relates coordinates and time in one frame to coordinates and time in another. So if you know two variables, you can always found two other variables. So you can use either pair of Lorentz transformations to solve this problem at once. Think of this as solving simultaneous equations. This is about solving simultaneous equations. You have two equations, two unknowns. The two equations relate four quantities, x, t, x prime, and t prime. So now you just solve everything at once as simultaneous equations. But let me just write things down. So we have x equals gamma x prime plus dt prime. We have t equals gamma v over c squared x prime plus t prime. We have x prime equals gamma x minus vt. And it's true, this relationship is true. If these are true, then this is also true. And then we have t prime equals gamma minus v over c squared x plus t. Okay? Just checking. Let's see. If you stare at these, what do we know? We know x prime and we know t. So it's convenient to use this one. Convenient. We don't have to use just that one, right? So for example, we can look at this pair. We know x prime, we know t, so we can first solve for, well, I guess you cannot see. We know x prime, we know t, so we can solve for x and then plug that x into here and use this t to find t prime. Again, this is just two unknowns, two equations situation, so you solve simultaneous equations. But this one is convenient, so we have 0 equals gamma, well, v over c squared times x prime plus t prime, so t prime, which is what we know at the end of the day. The question asks for t prime. So let's answer that question. Equals minus v over c squared x prime. When we plug in the numbers, minus 0.6 c over c squared times 50. You don't need a calculator for this because you have to work in scientific notation. When you work in scientific notation, you usually don't need calculator. Times 50. Okay. So let me crank this out. I already did, but let's do this again. So 0.6 times 50 divided by 3. Well, it's 10. So that's minus 10 times 10 to the minus 8 minus 10 to the minus 7 seconds. Voila, we get what we got before, sort of in one shot. Okay, so, well, what about position of Bob's window? Remember, we actually didn't even need that in order to answer the question right now. But we can try to find position of Bob's window. i.e. x of event 2. you know, the most convenient one to use now is this one. Because we know that t is 0, x prime is 50. Right, so and then we use x prime equals gamma x minus vt. And so t equals 0, therefore x equals x prime over gamma. Hey, that's just length contraction. That's 50 over 1.25, that's 40. So you see length contraction is built into Lorentz transformations. You can also find x prime by other methods. So for example, I'm sorry, x. You can also find x by other methods. So we know x prime, that's 50. And we just found t prime. And gamma is 1.25. So try to use that. And again, you will also get 40 meters. So good. And that's your introduction to Lorentz transformations and an example of how to use it. Tomorrow, we'll spend probably the whole day using Lorentz transformations on other problems. There's one problem that I'm thinking of that we will digest. In fact, it will be continuation of this problem, just sort of taken further. We will ask more questions, and we'll keep putting Lorentz transformations to use. And then eventually we will move on to the next topic. Okay, so we're going well, and I hope you're following, hope you're watching videos. I'm trying to slow down to make information digestible. It's new and non-trivial, but remember, all these strange non-trivialities arise from the fact that speed of light is the same in all frames. If you have a flash of light and it's creating a spherical wave, the wavefront is spherical, the waves are moving in all directions at speed c, as seen from one frame. And then when you analyze it from another frame, they also see a spherical wave with the wavefronts moving at speed c. So this strange idea, which remember came from thinking about electrodynamics plus experiments, such as Michelson and Morley experiment, and there were others. The story is more involved than what I told you. That forced humanity into that strange idea that speed of light is the same in all frames. And everything else comes from that. And of course, keeping principle of relativity is sort of a sacred principle. Don't touch it. Principle of relativity must be true. And so from there, all this strangeness arises, which you see only at high speeds, but high in comparison to a human scale. And as I mentioned yesterday, these effects become pronounced when you look at events separated by short enough times. So if you have electronics, or if you have like GPS, then it's very common to have events that are separated by times, by time scale, so by intervals of time, for which time dilation, for example, is comparatively not a small effect. Okay, so we will continue as we go on. Have a good one. Bye.